students, today we discuss about the electric potential. First we have to define the electric potential. What is the definition of electric potential? It is defined as the amount of work done by an external agent in bringing a unit positive test charge from infinity to a particular point in the electric field without any acceleration is known as the electric potential. Let here is infinity, a unit positive test charge is plus del q. Is a unit positive test charge plus del q. It is bringing from infinity. This is some electric field. This is the electric field and this point is P. This is a particular point. Now I have to bring this unit positive test charge from infinity to particular point P. So what is the amount of work done? This is known as the electric potential. Means let W is the amount of work done in bringing a unit positive test charge plus del Q from infinity to particular point capital P. Then the formula of electric potential is according to the definition, per unit positive test charge means the work done W divided by plus del Q, because the W is the total work done for bringing or in bringing the unit positive test charge from infinity to that point. Therefore, per unit positive test charge, the total work done is W by plus del Q. And work done is a scalar quantity, charge is a scalar quantity, therefore electric potential is a scalar quantity and it is denoted by V. So mathematically, V equal to total amount of work done W divided by unit positive test charge plus del Q. That is the mathematical expression for the electric potential. Then I have to find out the SI unit of electric potential. The SI unit of work done is joule and SI unit of charge is coulomb, joule per coulomb, or that is known as the volt. According to the name of scientist Volt, the potential SI unit of electric potential is volt. Means 1 volt is equal to 1 joule per 1 coulomb. Then the dimensional formula of potential, electric potential, from the formula V is equal to W by Q. The dimensional formula of W is M1 L2 T minus 2 divided by charge is 80. Now by solving this, I can find the value of dimensional formula electric potential M1 L2 T minus 3 A minus 1. Then the expression for electric potential at a point due to a point charge. This is 3 marks question. We have to find out the electric potential. We have to calculate the electric potential at certain point due to a point charge. Here from the diagram, this is point charge plus Q and this is the point P, point of observation, where a test charge plus del Q is placed. I have to calculate the electric potential at this point P due to this point charge. Let the distance between the point of observation where the test charge is placed and the point charge plus Q is smaller. As the both charges are positive, because test charge always positive and here I have taken the positive point charge. Therefore the electrostatic force is repulsive and the direction is away from the point of observation and they are separated by distance r. Now as the force is in this direction, therefore a displacement, linear displacement minus dr vector, because in direction is the opposite direction of the force, electrostatic force, therefore it is negative. And this point F, infinity point, infinity means from the infinity a unit positive test charge is bringing. Then work done by the field force on the test charge plus del Q for an elementary displacement, elementary or linear displacement minus dr vector is, according to the formula or definition of work done, W is equal to force vector dot displacement vector. So dW is equal to, here dW, why I have taken dW? Because dr is the small elementary displacement. Due to small displacement, small work dW. dW is equal to F vector. Here the force is F vector and the elementary displacement is minus dr vector. Therefore dW is equal to F vector dot minus dr vector. Work done is the dot product of force vector and displacement vector. Then what is the angle between the force vector and the elementary displacement vector? As both are in opposite direction, therefore the angle between them is 180 degrees. Now, according to the formula of dot product that I have taken here, minus f dr cos 180. What is the value of cos 180? Cos 180 is equal to minus 1. Minus minus becomes plus f dr. What is the value of f? F means electrostatic force. Separation between them is r. F is equal to formula according to Coulomb's law 1 by 4 pi epsilon naught q into plus del q or q into del q divided by r square 1 by 4 pi epsilon naught q del q by r square into dr. This is the value of dW. I have to calculate the total work done. Therefore, I have to integrate both sides. Integration, when I will take the integration, then the work done dW work done changes from 0 to W. Whenever the work done is 0, then at that time the test charge is at infinity. When the total work done is W, at that time the point of observation of UV positive test charge at certain distance small r from the point charge. Therefore, I have to integrate the left side dW from 0 to W, but right side from infinity to r. Means at infinity the total work done is 0. At certain distance r, the total work done is W. Therefore, infinity to r 1 by 4 pi epsilon naught q into del q by r square dr. Now here variable dr is the r is the variable, therefore dr and r square is the integrating, but 1 by 4 pi epsilon q plus q del q is the constant that becomes outside. And now integrating r to the power minus 2 dr from infinity to r, definite integration here w equal to q into del q divided by 4 pi epsilon naught integration of r to the power minus 2 according to the formula of integration x to the power n dx is equal to x to the power n plus 1 by n plus 1. So here similarly n is minus 2, therefore r to the power minus 2 plus 1 by minus 2 plus 1 from infinity to r. That is definite integration. W is equal to q del q by 4 pi epsilon naught. R to the power minus 2 plus 1 means minus 1 by minus 2 plus 1 means minus 1. That is, I can write it minus 1 by r. From infinity to r, lower limit is infinity, higher limit is r. Now I have taken common minus negative, minus q into del q by 4 pi epsilon naught. But first I have to take the lower limit, upper limit, then lower limit, that becomes 1 by r minus 1 by infinity. 1 by infinity value is 0, therefore W equal to minus q into del q by 4 pi epsilon naught into 1 by r. This is the value of work done. But according to the definition of electric potential, V is equal to W by Q. But here opposite direction, therefore V is equal to minus W by del Q. Now minus this minus plus 1 by 4 pi epsilon naught by del Q cancel out Q by R. This is the required formula for electric potential due to positive point charge. V is equal to 1 by 4 pi epsilon naught Q by R. But similarly for negative point charge, the electric potential can be written as V is equal to 1 by 4 pi epsilon naught minus Q by R. This is the required expression for the electric potential for the negative point charge, and this is the required expression for the electric potential for the positive point charge. These two are remember work done can be negative or positive, therefore electric potential also can be negative potential or positive potential. When it is positive point charge, the potential is positive, whenever it is negative point charge, the potential is negative. Next, the net electric potential at any point due to a system of point charge. This is 2 marks question. What is the net electric potential in total electric potential at certain point P, where a positive base charge plus del Q is placed due to a system of point charges. I have taken here a system 4 point charges. One is plus Q1, another is minus Q2, one is plus Q3, another is minus Q4. And the distance of plus Q1 from the point of observation is R1. And the distance of minus Q2 point charge from the point of observation is R2, and the distance of plus Q3 point charge from the point of observation is R3. Similarly, R4 is the distance from the point of observation to the point charge minus Q4. I have written here, let V is the net electric potential or total electric potential at the point P due to the system of point charges plus Q1, minus Q2, plus Q3 and minus Q4. Similarly, for N system we can also calculate. So let I have taken here V1 is the electric potential at the point P due to plus Q1. V2 is the electric potential at the point P due to minus Q2. V3 is the electric potential at the point P due to plus Q2. And V4 is the electric potential at the point P due to minus Q4. So according to the formula or the expression in the previous section, that V1 is equal to 1 by 4 pi epsilon naught Q1, because this is positive point charge, therefore the electric potential is positive, Q1 by distance R1. Similarly, V2 equal to, as it is a negative point charge, therefore electric potential V2 is equal to 1 by 4 pi epsilon naught minus Q2 by R2. Similarly, V3 equal to, as the point charge is positive, V3 is positive, that is equal to 1 by 4 pi epsilon naught Q3 by R3. And V4 equal to 1 by 4 pi epsilon naught minus Q4, because the point charge is negative, therefore the electric potential V4 is negative, minus Q4 by R4. If this is positive, then this is also positive. If this is point charge is negative, the electric potential is negative. Now the net potential, what is the net potential? The sum of the algebraic sum, because electric potential is a scalar quantity, therefore the total or net electric potential is the algebraic sum of the electric potential due to the system of point charges. So V equal to V1 plus V2 plus V3 plus V4. So I have taken V is equal to, I have replaced V1 as the formula 1 by 4 pi epsilon Q1 by R1. V1 is equal to 1 by 4 pi epsilon naught Q1 by R1. V2 equal to 1 by 4 pi epsilon naught minus Q2 by R2. V3 equal to 1 by 4 pi epsilon naught Q3 by R3. Similarly, V4 equal to 1 by 4 pi epsilon naught minus Q4 by R4. And by taking common, what is the common thing? In all V1, V2, V3, V4, 1 by 4 pi epsilon common thing, then becomes remaining part Q1 by R1 plus minus Q2 by R2 plus Q3 by R3 plus minus Q4 by R4. This is the required expression for the net electric potential at the point, any point or point of observation due to the system of point charges. But I am, for my system, there are 4 point charges. This is 4 point charge system. For similarly, for n point charge system, you have to calculate the different potentials V1, V2, V3, Vn. Then the net potential can be replaced by V equal to V1 plus V2 plus V3 up to Vn, and similarly the process goes on. Next part is the derivation for electric potential energy possessed by a point charge placed at any point in the electric field. This is another 2 marks question also. We have to calculate the electric potential energy. Electric potential energy means the total amount of work done in bringing you positive test charge. The total work done means, as according to the definition, V is equal to W by Q or del Q. This W is known as the electric potential energy. Means W is equal to V into del Q. But here potential energy is denoted by capital U. The left here is the electric field, a point P where a point charge plus Q is placed and having the potential is V due to the point charge. So now we have to calculate the electric potential energy due to the point charge plus Q. So if plus Q charge is placed at any point P in an electric field having potential capital V at that point, then the potential energy possessed by plus Q charge at P is, according to the definition, U is equal to plus VQ or plus QV. Any one you can write plus VQ. Q is the point charge, V is the potential. Then what is the SI unit of electric potential energy? According to similar equation energy, then what is the energy unit of work done? That is joule. Now similarly the SI unit of electric potential energy is also joule. So now this is the formula of electric potential energy. Now we have calculate the mutual potential energy due to a pair of point charge. Here I have taken a pair of point charge. One is the plus Q1, another is the plus Q2. They are separated by a distance small r. Then the mutual potential energy means Q1 here. At the point Q1, the electric potential is V2 due to the point charge plus Q. Therefore, at the point Q1, this point, let this point is A and this point is B. At the point A, the electric potential due to plus Q2 point charge is Q2 by 4 pi epsilon naught R or 1 by 4 pi epsilon naught Q2 by R. And at the point B, the electric potential due to the point charge plus Q1 is V1, that is equal to Q1 by 4 pi epsilon naught R. This is known as the mutual electric potential. Mutual means at the point A due to B, at the point B due to A, and the separation is R. Then the mutual potential energy at the system of pair of point charge U is equal to, what is the potential energy? Potential energy means Q into V. The mutual potential energy at the point A or B, similar B is A, similar point left Q2. Q2 is the charge at the point B. Therefore, electric potential at the point A due to Q2 is Q2 into V1. And similarly at the electric potential energy at the point B due to Q1 is Q1 into V2. So here I have taken any one, U is equal to Q2 into V1, and now Q2 into V1. How much? What is the value of V1? That is Q1 by 4 pi epsilon naught R. Q2 into V1 replaced by Q1 by 4 pi epsilon naught R. That it can be written as 1 by 4 pi epsilon naught Q1 into Q2 by R. This is the required expression for the mutual potential energy. Start. Next is relation between the electric field intensity and the potential. This is the one mark question. What is the relation between the electric field intensity E vector and the electric potential means V? Let the work done on unit positive charge for elementary displacement dr vector. Here a point charge plus Q is placed. P is a point of observation, and the linear displacement dr vector towards the positive point charge, and the direction of electric field intensity in this direction. The angle between them is 180 degree. Now dV is equal to E vector dot dr vector, or dV is equal to E dr cos 180. Dr equal to minus 1, that dv is equal to minus e dr, or e is equal to minus dv by dr. dv by dr is factor known as the potential gradient. Potential gradient means derivative of the potential with respect to displacement is known as the potential gradient. So therefore, the relation between the electric field intensity and the potential is the electric field intensity is equal to the potential gradient, electric potential gradient. Remember this formula for numerical purpose. Then I have to calculate the total work done, total potential when a point charge is replaced from certain point to another point. Let a point charge is replaced from certain point whose position vector is r1, another to r2. Initial point is r1, final to r2. Now dw by small displacement dr. Now dw is equal to, according to the formula, f dr, that is 1 by 4 pi epsilon q1 q2 by r square dr. Now w is equal to integrating both sides. This side integrating from r1 to r2, initial to final position. Now from r1 to r2, 1 by 4 pi epsilon naught q1 q2 by r square dr. As q1 q2 constant, 4 pi epsilon also constant. Therefore w equal to q1 q2 by 4 pi epsilon naught from r1 to r2, 1 by r square dr. Or that can be written as q1 q2 by 4 pi epsilon naught. 1 by r square means r to the power minus 2. Integration, taking integration r to the power minus 2, that is equal to r to the power minus 1 by minus 1. That can be written as minus 1 by r. From initial position to final position, that is r1 to r2. Or I am taking common minus negative sign, the minus q1 q2 by 4 pi epsilon naught whole into upper limit by lower limit, the 1 by r2 minus 1 by r1, or taking negative inside, that becomes negative positive, that becomes positive negative negative. Now I can write w is equal to 1 by 4 pi epsilon naught q1 q2 by 1 by 4 pi epsilon naught q1 q2 whole into, this becomes positive, this becomes negative, 1 by r1 minus 1 by r2, or w equal to means q1 q2 by 4 pi epsilon 1 by r1, this is w1. 1 by 4 pi epsilon q1 q2 by r2, this is w2. Therefore that can be written as w1 minus w2. Or similarly, as w is equal to v into q, therefore v can be written as v1 minus v2. V, this is the difference of the potential and is known as the potential difference between the 2 points. This is the total work done between the 2 points. This is the potential difference between the 2 points. This is the required expression for the electric potential, and this is the required expression for the work done. Here, this formula, the relation between the electric field intensity and potential for numerical purpose. Whenever the velocity is given in the form of displacement, then you have, if the question is find the electric field intensity, then you have to take the derivative of the potential with respect to length or displacement. And this term, remember, this term is known as the potential gradient. Potential gradient means differentiating any physical quantity with respect to length. It's like velocity gradient. Velocity gradient means derivative of velocity or dv by dl or dr or dA with respect to length. This is known as the velocity gradient. Similarly, potential gradient, derivative of potential with respect to length or here elementary displacement, that is dr. Therefore, I have written here E is equal to minus dv by dr. Here velocity potential is the scalar quantity. This is vector, this is vector. So similarly, this equation is satisfied. Now here from this equation, whenever the potential difference is in question, then you have to put the formula V is equal to V1 minus V2. So work done, whenever there is work done formula, so you can put the formula W is equal to W1 minus W2. This is the required expression. Next is your equipotential surfaces. Equipotential surfaces means the surface or the locus of all the points having same potential in an electric field is called equipotential surface. The locus of the points, or having similar definition, second definition, the surface of every point at which the electric potential is same or equal in an electric field is called equipotential surfaces. Equipotential surface means the potential having same in each and every point in the electric field, then they are known as the equipotential surfaces. Or the locus means the line of force, or in the electric field lines, if I join the locus of the points of the lines of force, if they have the same potential, then the equipotential surfaces. Equipotential means equal potential surface. So this is the required definition of equipotential surface. The question is, what is equipotential surface and what are its types or what are its properties? Types means there are three basic types of equipotential surfaces. Here I have drawn. This is plane surface. Plane equipotential surface means whenever the uniform electric field. For uniform electric field, here I have drawn the uniform electric field E vector. Then the equipotential surfaces are in the plane shape. This like the shape of the equipotential surface is like this. This is the planar shape. Therefore, this is known as the plane equipotential surface. Next is your spherical equipotential surface. Spherical equipotential surface is for point charge. Whether it is positive or negative. Whenever it is positive point charge plus Q, then the equipotential, the electric field lines in the direction outside. Therefore, the equipotential surface is locus of the points circle. These are the spherical. Therefore, the shape is spherical in shape. Similarly, for negative point charge minus Q, the electric field line's direction is inward towards the point charge minus Q. Therefore, the shape of the equipotential surface is also spherical in shape. The spherical is in both for positive point charge, also negative point charge, and here for linear charge body, cylindrical charge body, the shape is spherical in shape, like this. Cylindrical in shape. This is a linear point charge. And the electric field line's direction is away in this direction. Then the locus of the points are cylindrical in shape. Linear here point charge, linear point charge. At this, if I draw the electric field lines, then this are in this direction because positive, totally positive charge. Here positive. Positive means one end or one terminal at the one terminal. This is the same. Here electric field lines are like this, and another terminal the electric field lines are like this E vector in this direction. If I join them, the spherical for similar point charge. Here spherical. Then totally it looks like a cylindrical in shape. Therefore, the equipotential shape of the equipotential surface is cylindrical in shape. The important property of equipotential surface is that as the potential is same each and every point, therefore the potential difference or difference of the potential is always zero in the equipotential surface. The total potential difference, because the total each and every point here, total electric potential is same at every point. Therefore, the total electric potential difference means V1 minus V2. Let here potential is V1, another point is V2. then as V1 equal to V2, but according to the definition of potential difference, V1 minus V2, then V1 minus V2 is equal to 0. Therefore, the total potential difference at each point on the equipotential surface is always 0. This is the all about the potential or electric potential. Remember in electric potential in this chapter, electric potential and capacitance, capacitor. This is another part of capacitance. This is electric potential. In electric potential, you have to calculate the electric potential energy. Electric potential energy may be positive or negative. It depends upon the types of point charge. Where the point charge is positive, then it is positive. If the point charge is negative, then it is also negative. Similarly, potential can be positive or negative. If the point charge is positive, then the electric potential is positive. And if the point charge is negative, then the electric potential is also negative. The potential is measured in volt and energy, potential energy is measured in joule. And potential gradient, its unit is volt per meter. Potential, the SI unit of potential gradient is volt per meter. Means E is equal to minus dV by dr. That means the electric field intensity unit is Newton per coulomb. That is also equal to volt per meter. Remember only the formula. Then you have calculate the dimensional formula and unit. This is the required definition.